All right, so good afternoon, everybody. My name is Maxime Martinasso. I'm the head of engineering at CSCS, and I will give you a site update. You know, site is just next door, but you know, an update is always good. So, as you know, 2 years ago we have announced the Alps machine together with HP and NVIDIA. And the question that you all have is, where are we now, today, 2 years after? And you see, it's there. But partially there. So we have already in the machine room some cabinets. So these are basically the multi-core AMD CPUs, and we'll do a scale out of the machine with using the Grace Hopper technology from NVIDIA. So what kind of scale out? So you remember that we have the pit-dense machine, which is roughly 5,000 nodes with CPU and GPUs, and another partition with CPUs. The Alps machine will be very similar in size. It will be about 5 Grace Hopper modules, and the CPU partition, as I've shown before, in the machine room. If you have questions, please interrupt me. So the Grace Hopper Superchip, so is manufactured by NVIDIA. So it has a Grace ARM CPU, and it will be connected to the special chip-to-chip NVLink. I'm sorry, I'm not a marketing guy. To the Hopper GPU, and so I put some numbers from NVIDIA. So this is a slide you can find on the white paper. So they have a nice white paper about this hardware configuration, and you can see that what they show is the bandwidth. Strange, you know. So you can see the nice HBM3 bandwidth, for instance, and there will be this special link between the CPU and the GPU on the same chip. Okay, and the memory also is to mention that it's not DDR, it's LPDDR, same kind of memory you find on your phone. Okay, but the infrastructure at CSCS is not only limited to what we have here. Actually, we have also part of infrastructure is at Lumi in northern Finland. So this remote dot here, I was there last week. It's very cold, I can tell you that. It's minus 20 degrees, it's very cold. But anyway, so this machine is basically a large couple of hundred petaflop machine based on AMD hardware. And it is basically located in a paper mill, okay? And this is 2 reasons for it, because they have the power, free power from hydro, and also carbon-free power, up to 200 megawatts. So here, for instance, at Lugano, we can go to between 20 and 30 megawatts. I'm not sure we can reach even 30 megawatts. Here they have already an order of magnitude bigger, to which means they can host much bigger petaflop machine. And as you can imagine, they have a kind of a free cooling, because you open the window and everything is cold. Joking. All right, so this is for the infrastructure, but CSCS is not an infrastructure. Actually, we have most of our engineers more on the software part than on the system part. And actually, most of our system engineers that I see many of here in the room, are also having quite a lot of work to do in, developing tools, as this was shown this morning, to manage the machine. So what we are doing is we are going on a journey to consolidate the different systems that we had in the past into one infrastructure. And we have started that journey with pit-dense, where basically initially we had only the user labs, so the universities doing HPC, and later we added the worldwide LHC computing grid, so the CERN. And this one have a specific stack, and therefore to be able to have those guys running, on the same environment as a user lab, we had to use containers, and that's why we have developed containers technology also internally. But now we are actually decoupling those two, and they are decoupled now in the new infrastructure. Oppositely, there were, we were doing with Metro Swiss the production weather forecast for Switzerland, and that was running on that machine with GPUs. Called Arolatsa, that's the name of the machine, and was the Cosmo model for weather prediction. And this is moving towards a new platform called Icon 22, because we're changing the model to the Icon model, also running on GPUs. We will have other platforms on the machine, so we have everything related to SKA, CTA, to radio astrophysics or astronomy, material clouds, for the materials creation and property detection, and the weather and climate. So not only the weather forecast, but also the climate analysis. And all of those platforms will be running on one large infrastructure. And the question is, how do you manage, to have all these different workflows, all these different schedulers, because the scheduler will be different. One can be using Kubernetes or Orchestrator in that case, or they can have their own separate configuration. So instead of having one large scheduler or platform where you have to tailor to find a compromise between all the different use cases, here we're building dedicated platform for every use cases. And how we do this is what I'm presenting now. So actually, Felipe yesterday hinted part of it. So he hinted the part in the middle here. Explain it. So we're building a technology called Versatile Software-Defined Cluster, or vCluster in short. And this technology is a set of tools, it's a set of scripts, it's a set of custom developed software that we're doing at CSCS. And there is 3 parts related to this. So there is a user environment management, there is a platform and service management, and there is infrastructure as code. Okay, so that are the 3 main pillars that you can find, and I will go over all of them in details. But as the name suggested, you can understand what they mean. So this what I'm presenting here is work in progress, as you have seen this morning with Felipe, yesterday morning with Felipe, for instance. We have some publication coming up related to this work. But basically, as I said before, on the PITSDYNE model, you have only one single environment, in that particular case, based on the CRE PE, to the programming environment, but was there for all the users. In this technology that we're building now, you will be able, as a user or CSCS, to load your own programming environment. And in fact, you will get to a very thin CRE OS and some platform services image, and you will be inside a container. And in that container, you will be able to easily deploy your environment, which will be basically a squash FS file that you will mount, to be precise. And basically, in that case, as a user, you will be independent on what is installed on the system in terms of compilers, debuggers, and things like that. So that's one of the aspects that we're working on. So we have a proof of concept already. I was a bit more than proof of concept. I think we reached MVP already for this work. There's still some details that need to be fixed. The second aspect is what Felipe has presented yesterday. So it's a platform and service management. So in that case, there is two main points. There's the provisioning of a cluster. So how do you, get the resources? And for that, they are building pipelines to talk to the infrastructure. And this is exactly what we call the south part. So the connection, because this layer is in between the two. So there is a connection from the south part from the infrastructure. And for that, there is work on having APIs, high-level APIs, because what we get from the CRE HPE management system is pretty low in terms of what you can do. And also provide this thin layer of a base image and the OS. From CRE or HP in that case. And the other part, which is what we call the north part, is related to what you build on top of this infrastructure in terms of services. And this is what consists of the platform. And that's, of course, services like Resource Manager, Slurm, or web-facing API, or these kind of things. They would get this software from and configuration from an artifact repository, and they, as I explained, they will be able to manage all those services using an orchestration engine called Nomad. And this is at that moment that as a user you will get inside the container without knowing it. That's what we call container first for users. And we do that for having an abstraction layer to be sure that, for instance, what you get inside the container is consistent. independently of the platform you're running on. Okay, so like you mount your file system and you bind mounts and stuff like this inside it. But the issue that you get is maybe you need some low-level, libraries or drivers that are on the kernel level, so not in the container. That's why we use these OCI hooks that we have developed within the Saurus to propagate this. And as I mentioned, Felipe explained this tomorrow or today. Alberto is tomorrow, today? Tomorrow, sorry. So Alberto tomorrow will present this injection of libfabric, for instance, so low-level library inside a container, and show that we get fantastic performance and more reliability. Continue, Alberto. Okay, and the last part is infrastructure as a code. So in an Alps machine, you have what we call the management plane or control plane, which is a microservice architecture of different services to manage the system. And the compute plane, what's where the compute nodes are, basically, and the management plane basically updating the status of the compute plane in short. And here, as I said before, we provide some high-level APIs because this microservice architecture is pretty low-level, so some workflows being built. We will have multi-tenancy, so basically you label some resources and you isolate the network with a slingshot, which is quite important. And as a second need that we have is when you do an upgrade, you don't want to tear down all your platforms, so we need what's called a zero downtime upgrade, where you can update components independently. And this is what we're doing together with HP. All right. In the past, we have been developing those two products, so Firecrest and Saurus, and we're still developing, but I just want to present them again to remind people. So Firecrest is basically a REST API to access the supercomputing system. So it has a Python bindings, which means that you can write Python code on your laptop, execute it, and that will fire a job or move data to the supercomputer. And Saurus is a container engine. And if you want more about it, Alberto is there, so it's good. And basically what it does, as I said before, the key differentiation for Saurus is that it uses OCI hooks. So the plugins that at runtime will update the container by injecting, devices or libraries to be able to have in non-HPC specific containers the right tools to use the HPC hardware. Okay, and they fit in the big picture of things. So they fit like Firecrest will be on top. Well, actually, Firecrest is also a service in the platform, but the usage will be made by scientific workflows. So they will have a consistent way. Instead of using SSH, to connect to the machine and execute commands, they will have a proper identity and access management, security check, and a proper interface. So you will know what you get at the output because it will be pre-formatted as JSONs. And as I say, Saurus will be there to, inject all the OCI hooks to be used. Because OCI is a standard, so you can also use OCI hooks with any other OCI compliant runtime, container runtime, to inject the right needs from the OS providing, from the infrastructure to the user environment. That's where you want to see it, because that's where you want to have your API to use the libfabric for slingshot, for instance, which is provided in these OS libraries. And that's my talk. So that's the update. I have 5 more minutes for questions, I suppose. So any question? Please?
If the container for any reason failed, like you said that container.
Well, this is quite a detailed question for Felipe. I don't think Felipe is in the room, so let me think about it. If the container fails, I think your job just failed. I don't think there is a recovery mechanism at this stage.
I mean, I better will make it run.
Yeah, exactly.
There will be no fallback, no immediate fallback.
No, I don't think so. It's not what, I don't remember having talked about it. Yeah. and then you get into what if you run bare metal on the Cray OS with a very thin image. Maybe you cannot do much about it. Yeah, with it. Question, please.
And inside of the storage,
I was waiting for my question on storage. Thank you. Well, so okay, so let me try to find a good answer for that. So multi-tenancy for storage at this stage for us is not there yet. Okay. So I know there is some data company here doing some storage and multi-tenancy storage, but they have to be integrated with the slingshot aspect, and there is work in that direction, and we are, waiting for this to happen, and and we will see what we get at the end. But we have to be integrated with HPE for sure. This is.
yeah, but
Yeah, you will have the same as a computer. You will have a large storage infrastructure where you will carve on demand, or at least on demand, at least maybe not on demand, but in infrastructure in as a code way storage section for. Yes, you can say that. I don't like the word virtual because not necessarily exactly isolated, segregated storage and yeah, exactly, yeah. Please.
Am I correct in understanding that you will now transport?
Correct.
Will that save the capabilities that you are
That's a good question. So there is potential for this because we're using the same management plane, so we have the same low-level APIs, and we are in discussion with them to transfer our technology also to Lumi.
and do you expect
So I would say ideally yes. In practice, it will depend on the HPC workload they have, because some of them may be more tailored for different kind of hardware or different kind of scales that you can only reach in different infrastructure. But ideally, I would say yes. Ideally, you can imagine that with Firecrest, when you submit a job, you give high-level information about the job, number of nodes, GPUs or not, and based on that, and then you have to be careful of the data, if the data is at the right place. That's also one point which is you have to take care of. But based on this condition, you could automatically select the right infrastructure and even the right scheduler. Because if you use for one core for 1 hour, maybe you don't go to Slum, you go to an HTC high throughput computing scheduler. So this is why Firecrest in that level is important, because it is abstracting away from the underlying platform infrastructure. So so here we have providing the platforms, okay? So those platforms with a set, of user environments and a set of services is something that we provide to the user. So it's not like you go on the cloud and you get some VMs and then you can deploy what you want. It's not the goal. So we still have dedicated platform for dedicated science, in that sense. But you can reproduce those platforms and spawn those same platforms somewhere else, like on Lumi, for instance, so to have like identical platforms on the different systems. Yes. Yes, so exactly. So one of what we need here, that I didn't mention is one of bullet point which is missing, so I omitted it because I don't want to go in that direction, but you're forcing the cards in the hands. So it is, if you build a necessary abstraction level here, at the high level APIs that you're using, then it is just provisioning a cluster. And once you have your cluster provision, then you can just deploy on top of the other stack. Yeah. Of course, there is a part of, because we're talking about performance, so if you're on performance guarantee, you better get the same level of hardware capacity or even better. And there is a cost, of course, and the data movement, not to forget. Yeah, but you can imagine that if we shut down hubs for whatever reason, we can reconstruct all our platforms on the cloud, for instance, and they will be transparent for the users. It's a bit more complicated because some platforms are dedicated with scientific devices, and scientific devices from the edge are pumping the data directly to the center. So you have to reroute those pipelines too. But yes, basically it is what it is, yeah. Welcome.
Tagadam pam pam tagadam 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 pam pam tagadam tagadam pam 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 pam